Although the topic of acids and bases can be quite involved, I will try to simplify it for you in this video lecture to include just the basic information. You have likely all heard of acids and bases and probably know a little bit about them. When you hear the terms acid and base, you may think of things that are acidic, like lemon juice, or basic, like baking soda, or you may think about the pH scale. We are going to talk about two different definitions of acids and bases here. The first definition is that acids are proton donors, while bases are proton acceptors. Remember that a proton is just a hydrogen ion, meaning it has no electrons and no neutrons. So acids are molecules that give up protons, while bases are molecules that take protons. An example of a common acid that you have used in the lab this year is hydrochloric acid, or HCl. As we have talked about, when HCl is in solution, it dissociates or breaks up into H+ and Cl-. Another way to show this very same reaction is to show the water that is involved. You can see here that the water molecule steals the H from the HCl, so that the water becomes H3O+, and the HCl is left as Cl-. Both reactions show the same thing, but the one on the left is just more simple because it doesn't show the water that is involved. We can label each reactant and product in this reaction. You can see that HCl loses a proton in the reaction. We know that acids lose protons, so HCl must be the acid. Once the acid has lost its proton, it is left as Cl-, which is known as the conjugate base. So the definition of a conjugate base is the thing that remains after an acid has lost its proton. You can see that H2O gains a proton to become H3O+ in this reaction. Because H2O is accepting a proton, it is the base and H3O+ is the conjugate acid. The definition of a conjugate acid is the thing that results from the base gaining a proton. HCl and Cl- is known as a conjugate acid-base pair. H2O and H3O+ is another conjugate acid-base pair. Let's look at another example of an acid. HNO2 is nitrous acid. You can see that it dissociates into H+ and NO2-. Similarly to the example above, we can look at the reaction of HNO2 with water and label the conjugate acid-base pairs in this reaction. H2O steals a proton from HNO2 in this reaction. Therefore, H2O is a base and H3O+ is a conjugate acid. Because it loses a proton, HNO2 is an acid and its conjugate base is NO2-. An important takeaway here is that H3O+ and H+ are essentially the same thing. You will see H3O+ written when the water is shown in a reaction, and H+ written when no water is shown in the reaction. One other difference you may have noticed about the two reactions discussed here is that one of them has a one-directional arrow, while the other one has a two-directional arrow. There is some significance to that difference, and we will discuss it on the next slide. Strong acids and bases do dissociate or break apart completely in solution, while weak acids and bases don't dissociate completely in solution. Therefore, if you were to look at a solution of a strong acid, as seen on the left in the diagram, it would be split entirely into its ions. In the little graph below, the circles, Ha stands for a strong acid. Because it is strong, it splits into H+, the proton, and A-, the conjugate base, so that there is none of the Ha left. A weak acid is seen in the right-hand diagram. As you can tell, weak acids do not dissociate much at all. Hb represents a weak acid, which only splits up a tiny bit into H+, the proton, and B-, the conjugate base. The majority of it remains Hb. We are going to talk about a bit of a different way to define acids and bases than we did a minute ago. Similarly to the last slide, acids have an H+ that can dissociate. HCl is a strong acid, meaning it dissociates into H+ and Cl- completely. Because it is a strong acid, no HCl remains after the dissociation, but there are large amounts of H+ and Cl-. H2SO4 is another strong acid. It also dissociates completely into 2 H+ and 1 SO4 2-. The definition of a base here is different than the one you heard a few minutes ago. While acids have H+ ions that can dissociate, bases have OH- ions that can dissociate. An example of a strong base is NaOH, which dissociates completely into Na+ and OH-. Another example of a strong base is CaOH2, which dissociates into Ca2+ and 2 OH-. We are now going to talk about the equilibrium constant for water, also known as Kw. Hopefully, this reaction and corresponding equilibrium expression looks familiar from our recent discussion of equilibrium. Let's look at what happens to water when it's left on its own. This may seem counterintuitive to you, but water actually does dissociate into its ions, H+ and OH-, just slightly. Most of the water remains H2O, which is why the H2O is written very large, but there is a small amount that exists as ions, which are written very small. If we were to write an equilibrium expression for the water equilibrium above, we would call it Kw, since it is the K for water. It would be written as the concentration of H+ times the concentration of OH-. Remember that it doesn't get put over the concentration of H2O, because water is a liquid and liquids don't get put in equilibrium expressions because their concentrations don't change. The K value for water in any aqueous solution is 1.0 times 10 to the -14th, which is a tiny number. Remember that a tiny value for K means that there are much more reactants than products, so the equilibrium lies very far to the left. Based on the equation above, we can see that the concentration of H+ is equal to the concentration of OH-. We could solve this equilibrium expression for either of those concentrations to see that the concentration of H+ and the concentration of OH- are both 1.0 times 10 to the 7th molar. We will discuss the meaning of pH and pOH on the next slide, but for now, know that you can calculate the pH by taking the negative log of the hydrogen ion concentration, and you can calculate the pOH by taking the negative log of the hydroxide ion concentration. Because the concentration of H+ and the concentration of OH- are the same, the pH and the pOH are both equal to 7. This slide will review the important acid-base equations you need to know, as well as talk in general about pH, pOH, acidity, and basicity. You may remember something about the pH scale for acids and bases. Essentially, pH is a measure of H+ concentration, which is an indication of how acidic or basic a solution is. The pH scale goes from 0 to 14. A substance with a pH between 0 and 7 is considered acidic, while a substance with a pH between 7 and 14 is basic. A substance with a pH of 7, like water, is neutral. A higher concentration of H+ leads to a lower pH, which means a more acidic substance. Be careful, as this is somewhat counterintuitive. Many people think more H+ means a higher pH, but it is the other way around. A higher concentration of H+ means a lower pH. As was stated in the previous slide, pH equals negative log of the concentration of H+. Kw, the equilibrium constant for water, is 1.0 times 10 to the minus 14th. It can be used for any aqueous solution in order to find the concentration of H+ and OH-. Similarly to the way that pH is a measure of the H+ ions in a solution, pOH is a measure of the OH- ions in a solution. pOH equals negative log of the concentration of OH-. The pH plus the pOH of a solution always adds up to 14. This concludes our acid-base lecture. We'll work on problems in class.